Pluto, once viewed as a far-off and baffling minor planet, was initially classified as a member of our solar system's planet group. However, remarkable discoveries from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They shared an astounding hypothesis, suggesting that Pluto could be on a collision course with Neptune. But how is this possible? And what could the consequences of such a massive impact be? Are we witnessing a rare cosmic event, or is there more to this looming disaster? Join us as we explore the potential outcomes of a Pluto-Neptune collision. Once considered an undeniable planet, but later downgraded to a dwarf planet due to its unique orbit, Pluto remains an object of great interest and study in the scientific community. Recent predictions from leading experts indicate that Pluto's orbit is dangerously close to that of Neptune's. This has prompted astrophysicists like Neil deGrasse Tyson and Michio Kaku to raise alarms about the potential for a catastrophic impact between these two celestial bodies, a scenario that could pose a significant threat to Earth. But how could this even be possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system, taking a staggering 248 years to complete a single orbit. Since its discovery in 1930, it has yet to complete even one full revolution. However, Pluto's orbital irregularities don't end there. Its orbit is highly elliptical, contrasting sharply with the nearly circular paths of other planets. Adding another layer of peculiarity is the inclination of Pluto's orbit, measured at 17 degrees to the ecliptic plane. This steep inclination means Pluto's path is much more extreme compared to that of other planets. Perhaps the most fascinating aspect of Pluto's orbit is its interaction with Neptune's. For approximately 20 years in each orbit, Pluto comes closer to the Sun than Neptune. This defies what we might expect from their relative positions in the solar system. Naturally, this raises the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influence of other planets. Pluto's unique orbital behavior was first examined shortly after its discovery. Astronomers were initially astonished by its unusual trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic, the mystery deepened when it was realized that Pluto's orbit indeed crosses Neptune's path. The fact that Pluto's orbit remains stable despite these apparent conflicts illustrates the intricacies of celestial mechanics. The study of this phenomenon involves the three-body problem, which seeks to understand the gravitational interactions between three bodies in space, such as Pluto, Neptune, and the Sun. This is akin to predicting the movements of these bodies based on their initial positions and the gravitational forces they exert on one another. In Pluto's case, this problem highlights how its orbit, Neptune's path, and the Sun's gravity interact in a complex manner. Terms like asymptotic libration, longitude libration, and the VSK oscillation help explain this. Astrophysicists have confirmed that the phenomenon of libration is critical in maintaining orbital stability between Pluto and Neptune. Libration ensures that when Pluto crosses Neptune's orbit, their relative positions are always at least 90 degrees apart, preventing a collision. Longitude libration refers to the horizontal oscillation of Pluto within its orbit, while vertical libration describes its movement above and below the orbital plane. This additional vertical separation provides further protection from a potential impact. Another key factor maintaining Pluto's stability is the VSK oscillation, named after scientists V. A. Steklov and colleagues who studied gravitational interactions between three celestial objects. This concept explains how Pluto, Neptune, and the Sun's gravitational interactions influence Pluto's orbit. The VSK oscillation helps us understand why Pluto's path, despite appearing chaotic, actually remains stable over incredibly long timescales. These mechanisms, libration, longitude libration, and the VSK oscillation, work together to ensure Pluto's orbit avoids collisions with Neptune. This interplay of forces demonstrates how complex celestial mechanics can stabilize even the most seemingly unpredictable orbits. Understanding the three-body problem is essential for unraveling the dynamics of these orbits, not just for Pluto, but also for other distant objects in our solar system. Numerical simulations from the late 1980s revealed that while Pluto's orbit is stable for now, it shows minor variations that could lead to significant changes over millions of years. These simulations also demonstrated how the gravitational forces of giant planets like Neptune, Jupiter, and Saturn contribute to stabilizing Pluto's path. In fact, Pluto has a unique resonance with Neptune, completing 2 orbits around the Sun for every 3 orbits Neptune completes. This resonance maintains the stability of Pluto's orbit. However, Neptune is not the only planet influencing Pluto's trajectory. Jupiter, with its immense gravitational pull, also plays a crucial role in safeguarding Pluto's orbit. Saturn's influence further enhances this cosmic stability. Simulations show that Jupiter alone has enough gravitational force to keep Pluto's orbit steady over billions of years. It is as if Neptune, Jupiter, and Saturn are working together to prevent Pluto from encountering any significant risks in space. These gravitational interactions are vital for maintaining the overall stability of the solar system, preventing chaos that could arise from objects like Pluto colliding with other planets or being ejected from their orbits. The significance of these gravitational forces extends beyond Pluto and Neptune. The study of these interactions sheds light on the larger cosmic order, revealing how even minor forces can have profound effects on the stability and motion of celestial bodies. Without these stabilizing forces, the solar system would likely be a far more chaotic place. Objects like Pluto could collide with other planets or be expelled from their orbits, leading to unpredictable consequences for other celestial bodies. Given these intricate and stabilizing forces, why are scientists like Neil deGrasse Tyson raising concerns now about a potential Pluto-Neptune collision? Tyson, a renowned astrophysicist, is famous for his role in the reclassification of Pluto as a dwarf planet. His views on Pluto's orbital dynamics continue to evolve as new information emerges. Tyson argues that the reclassification of Pluto was not a demotion, but a necessary adjustment as our understanding of the solar system has grown. He views Pluto's unusual orbit and interactions with Neptune as opportunities for continuous scientific discovery, acknowledging the inherent unpredictability of space. While Pluto's orbit is currently stable, Tyson recognizes that future changes in gravitational forces, whether from the Sun, other planets, or unknown cosmic influences, could lead to unexpected alterations. This uncertainty serves as a reminder that even the most stable systems are subject to change over vast periods. The potential for a Pluto-Neptune collision, while unlikely in the short term, highlights the need for ongoing study of celestial mechanics. Understanding these dynamics not only deepens our knowledge of the solar system, but also helps us prepare for the unexpected in the ever-changing cosmos. Indeed, even frameworks that appear to be steady today are liable to change. Tyson's advance notice about the chance of a Pluto-Neptune crash highlights the developing nature of how we interpret heavenly mechanics. While such a crash may not occur for billions of years, it underscores the significance of continuous research and adjusting our models as new discoveries are made. The investigation of Pluto's orbit is fundamental for understanding the broader forces that govern the solar system. Tyson's emphasis on future uncertainties calls for continued observation and study, allowing scientists to refine our understanding of how gravitational forces and interactions shape the fate of planets and dwarf planets alike. As we continue to study Pluto's trajectory and its potential for future changes, we are reminded of the unpredictable nature of space. Despite the current stability of Pluto's orbit, its future remains uncertain. The possibility of a collision with Neptune or a dramatic shift in its trajectory remains a distant but intriguing idea. As we learn more about Pluto, our solar system, and the universe itself, we continue refining our understanding of how celestial mechanics influence planetary and dwarf planetary paths. Pluto's future might seem uncertain, but each new study provides deeper insights into how our solar system operates. The delicate cosmic dance between planets, such as Neptune and Pluto, emphasizes the sheer complexity and wonder of the universe. Although Pluto's orbit may remain stable for millennia, there is always the potential for change, hidden within the chaotic forces of space. Pluto's journey through the universe is far from simple. Despite its current stability as a dwarf planet, it serves as a remarkable example of the complexities of celestial mechanics and the forces that govern the motions of bodies in the solar system. The fact that Pluto's orbit intersects Neptune's without causing a catastrophic collision challenges our conventional assumptions. This curious case invites further exploration into how various forces interact to prevent celestial objects from colliding. While Neptune's gravity is often seen as a primary influence on Pluto's orbit, interactions with other planets, particularly the massive gas giants, play a crucial role in stabilizing Pluto's path. Jupiter, with its immense gravitational pull, is essential in this gravitational interplay, helping to maintain the stability of smaller and more irregular objects in the far reaches of the solar system. Saturn, too, with its massive rings and gravitational influence, contributes to the overall stability of planetary orbits. These giant planets act as cosmic shepherds, keeping Pluto on its stable course despite the eccentricities of its orbit. Beyond the gravitational forces exerted by the planets, the Sun's gravity remains the most fundamental force, guiding the trajectories of all objects within the solar system, including Pluto and Neptune. The Sun's pull establishes the overall structure of planetary orbits and the relative stability of the entire system. However, the Sun itself is far from static. It undergoes various cycles of activity, such as solar flares and fluctuations in its magnetic field. These changes, though subtle over short periods, could influence the orbits of distant bodies like Pluto and might, over incredibly long timescales, alter how Pluto and Neptune interact with one another. The ongoing study of Pluto's orbit not only helps us understand the current structure of the solar system, but also provides valuable insights into the processes that shape the evolution of planetary systems over time. While Pluto is safe from a direct collision with Neptune at present, the dynamic nature of the solar system means that no orbit is permanently fixed. There are forces beyond gravity that can influence the motion of celestial bodies, and even minor perturbations in planetary orbits could lead to significant changes in the distant future. This chaotic motion is one of the defining characteristics of the universe, constantly evolving, shifting, and presenting new challenges for astronomers to decode. The possibility of a Pluto-Neptune collision, though highly unlikely in the short term, highlights the inherent unpredictability of stable systems over long periods. Modeling the orbits of objects like Pluto allows scientists to understand not only the current structure of our solar system, but also the mechanisms that could eventually reshape it. Simulations of Pluto's orbit have shown that even small changes in initial conditions can have significant consequences for its future trajectory. These tiny changes, when compounded over millions or billions of years, could potentially bring Pluto closer to Neptune's orbit. This raises intriguing questions about whether other dwarf planets or objects beyond Neptune might eventually experience similar gravitational encounters with larger planets like Neptune or even Jupiter. The outer regions of our solar system remain largely unexplored, and many objects are only partially studied. The complex interactions between these bodies offer a glimpse into the mechanisms that govern orbital stability and may ultimately determine the fate of the solar system. The future of Pluto and other objects in the outer solar system depends on a variety of factors: gravitational, physical, and perhaps even unknown influences that scientists are just beginning to fully comprehend. The intricacies of planetary motion provide a fascinating view into the long-term future of our solar system, a future where even the most seemingly stable systems can be altered by the forces of nature. In conclusion, while Pluto's orbit is expected to remain stable for the near future, the possibility of change driven by chaotic forces within the universe cannot be ruled out. The study of Pluto's trajectory offers valuable lessons not only about the current state of our solar system, but also about the mechanisms that may shape its evolution. By continuing to study Pluto and its interactions with Neptune, experts gain a clearer understanding of the broader forces at play and how these forces could affect the solar system in the distant future. The study of Pluto, particularly its interactions with Neptune and other bodies in the outer solar system, opens up many fascinating possibilities for the future of planetary science. Understanding the dynamics of these distant regions helps scientists develop models not just for our own solar system, but for exoplanetary systems as well. The same gravitational principles that govern Pluto's orbit could apply to planets orbiting distant stars, offering insights into how planetary systems evolve across the cosmos. As our technology advances and our observational capabilities improve, we can expect to learn more about the outer reaches of our solar system, the Kuiper Belt and the Oort cloud. These regions hold many mysterious objects that could offer clues about the early solar system and the processes that led to the formation of planets and other celestial bodies. The future of Pluto, though unpredictable, remains a captivating subject of research. The possibility of new discoveries, whether regarding its orbital changes or interactions with other celestial objects, ensures that Pluto will continue to intrigue scientists and the public alike. As we expand our understanding of the cosmos, Pluto, despite its small size, will undoubtedly remain a key player in the quest to unlock the secrets of the universe. In the broader context of space exploration, Pluto serves as a symbol of how much is still unknown about the universe. As we push the boundaries of our knowledge, whether through space missions like NASA's New Horizons or through advancements in theoretical astrophysics, we are constantly reminded of how much more there is to learn. Each discovery, no matter how small, brings us closer to understanding not just Pluto, but the entire solar system and beyond. In conclusion, while the fate of Pluto may seem uncertain, the ongoing study of its orbit and interactions provides valuable insights into the workings of the universe. Through continued observation and research, we will better understand the forces that shape our solar system and the celestial mechanics that govern the paths of the planets and dwarf planets. As we continue to explore, the mysteries of Pluto and the cosmos will undoubtedly reveal themselves in increasingly profound ways.